Hey guys, what's up? I'm Jake, or Ferris, or whatever you want to call me. Um, Today we're going to start making a Nintendo 64 emulator in Rust. Now, before we get started, I want to go over a couple things just to sort of start the stream and set the right expectations. So first of all, I did recently get over the flu. One second. There we go. Yeah, so I did just recently get over the flu, so my voice is a bit raspy, and that's going to be okay. We're just going to have to deal with it. You could say my voice is just as rusty as the code we'll write today, I guess, if you are into lame jokes and stupid puns. So, sorry about that. Yeah, so to set the right expectations. So I've written a few emulators before, and I really love doing this stuff, and that's all cool, but I've never actually done one for Nintendo 64. I've just... I know a lot about the system, and I love the system. I had one when I was a kid. Getting this for Christmas in 1997 was just the shit. And so I'm really excited to do this. But again, I have not done this before. I've also never worked with MIPS before. I've never done an emulator that had sort of, proper GPU, like with a rasterizer. I've only done ones that have, that are fairly timing critical, where you have some kind of pixel processor that is, pushing pixels at a certain rate and set registers, whatever. But I've never done one that's sort of this advanced before, so I'm really excited to do this. So we're going to be doing this in Rust. There's a lot of reasons why I chose Rust, but the primary one just being that I really like it. We need to write some really performance critical code to make this work at any kind of playable rate. And so we're going to need to use something like C or C++. And Rust also falls into that sort of category. If you're unfamiliar with Rust, go to rustlang.org, rust-lang.org. I'm a huge advocate for this language because I just think it's fantastic. It's really fun to use. It's a bit different if you're used to C or C++. It's kind of weird to get used to because it does some stuff like its memory management is automatic, and you kind of have to get used to how it likes to do things to be able to take advantage of that nicely. But it's really nice once you get used to it, and the community is absolutely fantastic. Everyone's super helpful in the forums, and it's really cool. So check that out if you're interested, and of course you'll be seeing a lot of it during this stream. Another thing about expectations is that I plan to start this first episode on a set time so people could see it and people would know when it was going to happen. Moving forward, I'm not sure that I'll be able to do that most of the time, but I do plan on recording this. I'm recording this one, for instance, and I will set up a YouTube account and dump all the videos there. So if you don't catch the streams, you'll be able to watch them there. But the idea is that I don't want to write any code without streaming it for this project. The caveat being that there's a lot of times where I only have an hour today or 2 hours today or a half an hour in the whole weekend to actually write any code. And I'll be really excited to work on this. So I'll probably end up streaming parts of this project, just kind of whenever I feel like it. So I'll push updates on Twitter when I'm going to do that so you can catch it. I'll try to, if you guys like this, I'll try to do it at a more regular time, but we'll just see how that goes. So I guess we'll just get started. So for the first project, we're actually going to be starting literally from nothing. I haven't even made the GitHub repo yet. That's another thing. This is all going to be open source, so you can follow along with that project even if you don't catch any of the videos. So we're going to be making that. Another thing that we're going to be doing today is we're going to start sort of where any emulator starts, and that's with the CPU. Now, I'm actually, like I said, I've never really worked with MIPS before, so I have no idea how difficult that'll actually be. But I expect it'll be really fun. So I'm really stoked to try that. So today we'll really just be, doing some bookkeeping kind of things, setting up the project initially, getting it so we can load our first ROM, one more thing, in terms of where you can get ROMs and stuff, I'm not a big fan of piracy, and I will not sort of tolerate anyone posting any links in the chat, so that will result in an automatic ban. If you post links to where you can pirate ROMs or something, I'll have to remove you just because that's not what the stream is going to be about. But if you have legally obtained ROMs, then you can follow along, and that'll be really fun. The first one that I'm going to be testing with is Ocarina of Time, which is an amazing game. And awarding fabulous prizes. Sorry, I got distracted by the chat because you guys are pretty funny. So I guess we can just get into it. The first thing we need to do is actually create the project and start coding. The next thing we need to do is be able to load a ROM. And the next thing we have to do is we have to go over, like before we start writing the CPU, or actually I guess while we start writing the CPU, we have to consider what the actual boot process of the N64 is. Now I have done a bit, I haven't written any code for the project before I started this, but I have done a bit of research because I'm very interested in the system. And so I know a couple things about it, but I'm also just going to try to Google Live if I can, you know what I mean? Just so you guys can see this entire process, because the whole thing that I want this to be about is about me learning how to do this, you guys seeing what this will actually be like. Someone in the chat asked, where do you legally get an Ocarina of Time ROM? As far as I understand, the laws, at least in the US, are such that if you own a cartridge yourself, you are actually you're entitled to owning that cartridge and also one backup, like a software backup of that data. So if you can actually rip the ROM yourself, you can have one copy of that. To the best of my knowledge. So that's where you would legally obtain one of those ROMs. I won't be going into that in any more detail, unfortunately. So yeah, let's do this. So we're on GitHub. Let's make this repo. I'm just going to call it something like Rustendo64. That'll be pretty rad. Yeah. And N64 emulator written in Rust. By the way, guys, my keys are very clicky. I believe they're Cherry MX Browns. If that becomes too much of an issue, I can switch to a quieter keyboard. But keep in mind that I would really like to not do that because I have pretty bad RSI on my wrists, and so this keyboard really helps out with that. So if we don't have the switch, that's better. Yeah, so we'll just create the repo. Bingo. So now let's go ahead and create the actual project. So I've got my terminal here. My terminal fonts, I can bump that up. We're literally starting from nothing here. I get like 18. That should be big enough. All right. Here we go. So I have my dev projects directory. Good to go. Yeah, let's do this. So when you make new, too much StarCraft. I actually play a lot of Stepmania because that's awesome. Ooh, Fury Hunter just posted a really good link. Here's a guide to using an N64 Game Shark to back up a game if you don't have a real backup device. I would recommend that. Yeah, so when you're going to start a new project in Rust, yes, Fury Hunter, also notice Mammon Machine. That happens to be my Super Nintendo codebase, and hopefully I'll open source that at some point. Yeah, keep getting distracted. Anyway, so when you start a new project in Rust, you use their Cargo build tool. Cargo is, if you've ever used Haskell, it's similar to Cabal, one of those kind of things. So we'll do cargo new -- bin, and this was called Rustendo64, which is the perfect name. And there we go. So cd Rustendo, and there we go. So if we do cargo run in that directory, boom, we have Hello World. So great, we have the project started. I'm gonna go ahead and push this to GitHub already. This git remote add origin. What? Oh, whoops. Git init. There we go. Yeah, and we got some stuff in here. Do a git ignore. We'll ignore the target directory because that's where Rust generates everything, and I think that's all we need to do. And there we go. Here's our initial commit. Yes, I pull up Nano for git ignore. That's the only time you'll ever see me use it, hopefully. Cool, so now we are set up. We are rolling. I'm excited. Yeah. By the way, the editor that I will be using is Emacs. The end. If I need to bump up the font size, please let me know. I think I tested this before and it worked okay, but you know, we'll see how it goes. So we have our Rustendo directory here now, and we're good to go. So this project now just has the .git folder, the .gitignore. Fury Hunter also posted something nice here. When you're something about the cargo log, I'll actually go over that in a sec. So we created our new Rust project and then also made a Git repository. So we have this .git directory and also the .git ignore for the files that we're actually ignoring. We're ignoring the target directory, which Rust will use to generate all the files into when we actually do like a run. The other files, there's a source directory with a main.rs in it, and I'll get to that in a second. That's actual Rust code. We also have the cargo.toml file, toml. What this has is just some different information about our project here. So you can see it says package. The name is the name that we specified. Here's a version. There's also an author. Pretty cool stuff. Then the last file is a cargo.lock. And when you do like a cargo run or something, Rust will pull down like all your dependencies and all that kind of stuff and store that in this lock file. In this case, it's going to be pretty barren because we don't actually have any dependencies yet. But there you go. As Fury Hunter says, you do want to upload the cargo.lock file for executables, for actual runnable projects or binary projects. And my understanding of that is that that's because you want to have like the very specific versions of those, even though you can specify like semantic versioning in your toml file. And you want to be able to package that up like that. Could also have to do with licensing, I'm not entirely sure. Library projects, you wouldn't do that. But anyway, all we need in our git ignore is the target directory. So we are ready to get started. So going to main, not much here yet, just prints hello world. Cool stuff. Another introduction to Rust. This is how you make a function, and this is the entry point to your program. So pretty simple stuff. I'm gonna go ahead and do a cargo run. There we go. Awesome. Cool, so we are actually already to start loading a ROM, I guess. So the first thing we're going to need here is to get we're going to specify the ROM on the command line here. So we'll do cargo run -- and then the name of the ROM. I'm getting bigger font, please. Let's do that. Let's do that now before I get too much into it. My faces. My default face. Let's go for like 150. I think. Is this better for the font size? I could probably go a little bit bigger. I guess for this first one, it won't be too rough to have a pretty big font size. For later episodes, this probably will be pretty rough. All right, this font should be more than big enough, actually. Cut that, bro. I guess this is 1080p. I'll put up more. Why not? Why not? Bump it up a little more anyway. Oh yeah. That's a font size. Okay. So let's go ahead and we're going to run the ROM. So do cargo run -- and I have this ROM in here. ROM 64 and Legend of Zelda. And cool, nothing happens because we don't do anything with it. Great. So now, whoops, dashboard. Now that we got all that set up, let's actually do this. The first thing we need to do is actually read the file name off of the out of the environment arguments. Now, another thing you'll notice is that I've been doing Rust for like 6-7 months now. And it doesn't really matter to me how long I do a language for. I always go to the documentation for stuff like this because I just forget stuff all the time. So you're going to see how good Rust's documentation is. There we go, if I remember how to speak. I'll go to rustlang.org and documentation. I actually haven't tried this new nav here, so that's pretty neat. But I want the references, standard library API reference. Here we're looking for a module called env, I believe. std env. So in here, there is a function called args, and that's what we want. Go ahead and set this up here. So what we want to do is we want to pull in std.env. So we'll do use std.env. Now we have that available. And it's customary to like pull in the module you're using here and then qualify all the names you use from there like this, rather than, so like I'm going to be using args. So I could either use this and then call args like this. But as far as I know, it's customary to do this and call env args instead. So we'll do that. Fun stuff. So another thing about Rust is that it's really good about error handling, and we're actually going to be, I guess, loading this ROM. That could actually fail for numerous reasons, and so we're going to be using some results. But actually, for now, let's go ahead and skip that, just because we, really only care about this one thing. So, yeah. So I'm going to go ahead and do this. Let file name is std.env args, and I don't think you can index the iterator that this gives you. Look at that. Oh, we can do env. Because the first argument is going to be the name of the program or something else. It's kind of non-deterministic depending on your platform. I always like to do baby steps. So I'm just going to go ahead and print the file name. Didn't work. Did not like. I did env. Yeah, because this is a function, so do that. That's file name didn't have display trait implemented, so we're going to use the debug trait instead. Yeah, okay. Let's also do unwrap. So this returned an option here, but we actually just want the thing that's inside, which I believe is a string, which is good. Now this should work if we do this. Yeah. Cool. Yeah, you guys will be seeing me make a lot of mistakes. As long as you code, you just never stop not making mistakes. Just got to deal with it. Cool, so now we have our ROM. Let's go ahead and read all the bytes from it. Now, I actually don't remember how to do this in Rust, so this is good. Let's navigate the docs. So std, I believe it's actually fs is the file system stuff, where you want a file from that. So is it fs file, or maybe it's IO? Here's fs file, the type. Yeah. Looks like there's a file create, file open. Looks like this is what we want. In read-only mode. Yep, that's about it. Thank you, Ferry Hunter. It is fs file. Use std.fs. We are going to want to use file here. So again, because this is just like the really like bootstrapping and very, very basics of the project, this is going to be a bit slow, but it's live coding. And as Ferry Hunter points out, that is exactly what we're going to be doing. File is fs. We'll do this. Do take fs. Fs file, open, file name. And we might run that. And of course, we want a reference to that as far as I know. Yep, there we go. Cool beans. Now we have the, I believe, is it a read all? Read to end will do it. Reads all bytes until UF in the source, placing them into buff. So let's do that. So we'll go ahead and make a file buffer. Is vec new. It's going to be a new vector. go ahead and remove this. Miku Hatsunen says, do you plan to keep unwrap in the final program or eventually replace them with custom error handling? I will do error handling for sure, because I think that's good to show in Rust, and also it's like using unwrap to me feels really disgusting, but it's easy to just get up and running with it. So we're just going to do that now. I mean, I don't want this to be too much about Rust and not enough about the emulator, so don't want to go too into detail right away. So we'll just create a new vector. That'll give us an empty vector. Vector is resizable. It's like a resizable array, or vector in C++ if you're familiar with that. Whoops. Clicked on something. There we go. And so now we're going to do read to end on the file. File read to end. This ampersand mute self, if you're unfamiliar with Rust, this means like this in C++. This means this is a instance member. Is that what it's called in Rust? I can't remember what they're called. I know that static function ends up being called associated function, but I think that's just because it's associated with the type and lives in the same space. Anyway, too much into detail. Right after I said I didn't want to go too much into detail in Rust. Yeah, so then we're going to give a mutable reference to the file buff, and doing that means we also have to make this binding mutable. And whoops, and this will give us a result of usize, and I guess that's how many bytes were actually written. Let's see. Yeah, what we're going to do is, I believe in Rust you do okay, let me look at result. For results, yeah, so we'll do unwrap here. So it didn't like that I used read to end on that file because I need to bring in file if I actually want to use, yeah. So this gets into something called traits in Rust. File, as far as I know, is, sorry, file is a data type, file is a struct, but it implements something called a read trait. And you need to, whoops, sorry, I had that wrong. Put that back. File implements a trait called read, and in order to use any of the methods on read, even if you already have the object, you need to use the trait itself. So that's going to be stdio read. And what's really cool about Rust is that this actually tells me all of this here. So this was my whole error right here. Compiling this. Error, no method named read to end found for file in the current scope, which is where I used it here. And then it tells me some nice helpful errors here, or extra messages. Items from traits can only be used if the trait is in scope. The following trait is implemented but not in scope. Perhaps add a use for it. Candidate number one for stdio, or candidate number one use stdio read. So that's exactly what we'll do, and that should make it work. Now it doesn't like that file was immutable, and that's true. So we'll make that mutable. And there we go. So I guess we read it all. I think because we used std right there, then that's why it's giving me that unused import warning. Yep, good to go. All right, so now we have a buffer that has all our data in it. Another thing I like to do is just let file buff is file buff. What I'm doing here is, if we split this up into chunks, we're getting the file name. We're going to go ahead and take that file and open it, and then read the buffer out of it. And this buffer is mutable when it's, or this binding is mutable. So we have file buff, and that's a mutable binding. Later, I don't actually want that to be mutable. So I'm going to rebind that to what happens to be the same name, but this is just getting another binding to it. That's not mutable. So that's one thing that's definitely different about Rust than something like C or C++, is that in Rust, everything is immutable by default, whereas in C or C++, it's all mutable. I really, really like that. So we're going to stick with it. Now, of course, I get a warning that it's unused. I'm actually going to go ahead and add a clear, and every time I run this, you can see actually more of what's going on. Cool stuff. All right, so now that we've actually read the buffer, what we actually want to do is hook up a CPU to this and actually start running it. But that's not actually the entire thing. Now, I don't really remember where I looked this up, but what we're going to do is we're going to Google for Nintendo 64 boot sequence. Lucky for us, we're doing Nintendo 64, which is a pretty well-known system, and a lot of people have done a lot of reverse engineering on the system already. And so we're going to take advantage of that because they've published a lot of their results. Now, when you're working with an old computer like this, you typically have, everyone knows you have a CPU, and you'll probably have some RAM as well. And of course, a bunch of peripherals, which are usually I/O mapped, and I'll get into what that means when that matters. But the thing is that you also have a couple other components in there usually, or at least that are part of those other components. So I actually want to take a look at, before I get too deep into that, I actually want to just look at like super high-level overview of the N64. So from the Wikipedia page, Wikipedia is actually super useful if you want to look up like tech specs for old computers, by the way. We have a lot of information here. If we look on the right in this column here, let me bump up the size of stuff here. Or is that different? How do I zoom in Safari? You get to watch Ferris not know how to use computers. That's always fun. Anyway, I'll just select it anyway. If you look on the right here, you'll see that there's this thing here that says CPU. It's a 64-bit NEC VR4300 at 93.75 megahertz. Awesome, so we know what kind of processor is in there. The graphics, SGI RCP, 62.5 megahertz. Now that we know that there's at least those two chips, I want to take a look at the board. The lock says, "Are you switching to Twitch for good?" I don't think so. I'll try live coding again next time, but this time it was just cutting it too close to when I wanted to start actually streaming, so we moved it to Twitch for now. Again, I'll like post all the videos on YouTube and stuff later, so which streaming platform I use doesn't matter that much to me, but I'd rather use live coding because it feels more focused on that specific thing. So let's go ahead. Nintendo 64 board. Google for that, right? Now, if we look at images, the Nintendo 64 is actually pretty barren when you look at it. This thing was definitely built to cost. I want to get a big image. Oh, image check. Let's get a different one. Oh yeah, this is a beauty. That full screen. Good stuff. I love looking at boards. Okay, so if we actually start looking at this, I don't know if you guys can see that. You kind of have to put your nose on the screen. But the first, if we look at the markings on these chips here, this first one says Nintendo CPU N08. Who knows what that means? Except that CPU, I don't know what the other numbers are. But this is the CPU, and as you can see, it's quite large. That's that first thing we read about in the tech specs. The second thing we read over here is the RCP. Now, I happen to know that RCP stands for Reality Coprocessor, which is just the most 90s name for something. Oops, let me click on RCP here on Wikipedia. Yeah, Reality Coprocessor. Reality Coprocessor, RCP, is one of Nintendo 64's two main chips, alongside the NEC VR4300, which is that CPU that we saw. RCP was developed by Silicon Graphics for Nintendo, specifically Nintendo 64 video game console. The RCP actually has two main components inside it: the Reality Signal Processor, RSP, which is going to be used for, it's basically a stream processor, and it'll be used for processing audio and also for processing vertices. Then there's also the Reality Display Processor, which is going to be used for actually rasterizing pixels. And that's, yeah, this will go into more detail about that. So those are the two main chips. As you can see, there's these large buses that basically connect those. We also see some connections over to the cartridge. And then we have these two chips here. These, as far as I know, are going to be RAM, just judging by not only where they are, but also the size of them and the fact that there's really not much more here. Miko Hudsonen says, are these streams like an hour each time, no matter how much work, or some chunk of work, no matter how long it takes? The latter. It's going to be some chunk of work, no matter how long it takes. Of course, this introductory one is just going to be, I just kind of want to stream until I don't feel like streaming anymore. It probably won't be that well set up, just because this whole project is going to be a pretty natural process, so I kind of want to, I don't know, just go and let it happen. Yeah, so those are sort of the main chips that we see here. The rest of the chips that we see, if we start reading some of the markings, we're actually not going to find stuff that's that interesting to us. A lot of this is looks like there's like maybe a serial input controller or something, or probably a lot of different like timing chips that will bring these actually out to the video output. But the whole thing is that this whole part right here, the CPU, the RCP, the RAM, and the fact that that hooks up to a cartridge, those are the things that we're mostly going to be concerned with. And maybe that's wrong, but that's my understanding so far. And that's pretty typical for an emulator. But the thing of it is that when the CPU starts up, it's not going to just be pulling data from the ROM instantly. So when a CPU usually runs, it's just like, you can imagine this infinite loop if you're coming from a software perspective, where you're going to get a byte from memory. You're going to interpret it, and you're going to do something based off of that. And those are called the different instructions, right? And in a system like this, like in older systems actually, like C64 or NES or Super Nintendo even, it's fast enough that every single CPU cycle, because these CPUs ran, like 1 to 3 megahertz, every single CPU cycle, it would go fetch data from the actual cartridge. So if you could imagine, there's direct lines from the CPU onto the cartridge. So like there's this main bus that data flows through, and it's the same bus that goes to all the RAM and all the other peripherals, but the cartridge slot is just directly attached to that bus. Because of the low clock speeds, it's totally fast enough to just have ROM chips on the cartridge that it will go and read every cycle. Or at least, as often as that particular CPU would actually read. For instance, like a C64 is only going to do that every 2 cycles at most. Z80 is going to be doing that about every 4 cycles, that kind of thing. In this case, we're going to be running at about 100 megahertz, or, for practical purposes, way faster than we would ever be able to do that with, as far as I understand. I believe that part of the RCP's job is also to move memory from the cartridge into RAM. Now, again, as we do more research, maybe that's wrong, maybe that's right, but that's kind of the mindset we need to have. So what that means for us is that when the CPU starts and it just starts running, it needs to get that code from somewhere, and it's not going to do that directly from the cartridge. Now, again, this is something that I've actually done a little bit of research on beforehand, but with a system like this, and also modern systems, there's usually a little sort of either watchdog processor or another sort of piece of silicon. It's usually built into one of these kind of chips. Probably it's going to be built into the RCP just because of cost. The CPU would have been sort of an off-the-shelf component, and in order to add anything extra into there would have been very costly. So it's doubtful that they might have done that, but they definitely would have had room to do it in the RCP because they were developing custom silicon anyway. So I'm guessing it's in here, but it might actually be in the CPU. We'll see. There's typically some kind of boot ROM and another kind of little, microprocessor that will actually move that data into memory, typically into like a specific place in memory, and then the CPU will sort of have its way with that. Another example of this is like I have a couple Chromebooks. I'll actually grab them. I've got these little Chromebooks here, and I'm actually doing a project on these where I'm trying to get them to run Linux, and that's of course proving to be difficult because Chromebooks, if you didn't know this already, they don't want you to boot Linux right off the bat, at least not most of them. So to actually get at that, you have to go and take out this write protect screw physically from the inside of the device. And all this other nasty stuff. But the important thing is, it ties back to this, is that there is a specific chip on that board that is the boot ROM. And the first thing that happens before this ever runs code from your hard drive or from any bootloader is it will go into that boot ROM and then read a bunch of code from there and start executing that. And that ends up being your BIOS. So that's how your BIOS is kind of stored. So we can think of this sort of whole thing as little BIOS. And the BIOS's job is to sort of take that data from the cartridge, or at least some data from the cartridge, move it to some specific place in memory, and then start executing that. So that's the process that we're going to have to do first. So that's why I googled N64 boot sequence. So I'm just going to click this first link. Let's see what we get. This guy thought he'd showed documentation he'd accumulated through his journey in low-level N64 emulation, having included various source code, blah, blah, blah. Another thing that we have to watch out for because I'm streaming is that if we do find any sort of confidential documentation, I may have to remove that. But we'll see. Emulation in terms of legality ends up being a bit of a gray area. In general, though, you're able to actually produce emulators. That doesn't really cause any problems. It's more the game piracy that causes you issues. And also, we're generally pretty safe from any legal action because this is such an old system, and any of the sort of industry secrets that these documents would have contained are no longer relevant and haven't been for 20 years. Man, it's been 20 years. That's crazy. So all I'm really looking for is the boot process because everything else is not going to be that interesting. So I just searched boot. Here's a little info about how the N64 boots up. It's quite widely known, but oh well, it can't hurt. Upon power on / reset, the N64 begins executing the IPL, initial program load, boot ROM, at physical address 0x1FC, lots of zeros. The boot code pretty much just initializes the hardware, does a few checks, and copies the cartridge boot code, cart offset 0x40 to 0x1000, to this very specific address into the RSP DMEM. We'll find out what DMEM is. I don't know what that is. And jumps to it. After this, the cartridge boot is in control, so it can vary, but the following is typically what will occur. At this point, the portion of the main program code is DMA'd to the 4-byte address specified at cart offset 0x8. I guess we'll find out what that is. This address, DMA, by the way, stands for direct memory access, and it's a way to just move memory from one part of the machine to another part of the machine without the CPU sort of intervention. Without DMA, you would have, for every byte you want to move, you have to read a byte from the CPU and then write it somewhere else. So the CPU is in lockstep with the DMA. If you have DMA, it's usually faster because you're not having to do read and write. There's usually a piece of hardware that can do both, sometimes at the same time. SNES actually does that, where if it's using the DMA, it actually has 2 buses and it's doing a read on one and a write on the other at the same time. So it's very fast. And the other advantage is that in some systems, you can still have the CPU be active while DMA is happening. I don't know if that's going to be the case here, but just some kind of thoughts, what I'm thinking as I'm reading this. This address is usually referred to as the boot address, offset, or program counter. This address is where the actual program will begin. Now, again, all of that comes from, again, I'm just sharing my thoughts. All of that comes from the cartridge boot code. So if we have a ROM, that's going to have that in it, as far as I know. Because I'm just assuming that the ROM I have is definitely like just a RAM dump, or sorry, a ROM dump from the cartridge, and so I'm assuming that it will have this in it as well. When it says cart offset, I'm also guessing that that's going to be from the beginning of the data buffer that we read. So what we're actually going to want to do, it looks like, is pull some of that code and just look at it and look at it and see if it actually looks like MIPS instructions, which will be fun. So what's interesting about this is that it does say it begins executing an IPL boot ROM, which means there is a boot ROM somewhere in this machine. I don't think it's going to be outside of one of these chips, quite frankly. It's probably going to be a hard-coded ROM that goes in there. Maybe it's this guy. It's wired up to the RSP. Who knows? But I doubt it's going to be one of those chips. And what that means is that pulling that is going to be hard. So like if we actually tried to find that code, it might be really difficult. Now, if we had that, it would probably be best to actually run the actual code because it might, set some hardware registers to specific values that the cartridge boot code might sort of expect to be there. But my guess, actually, is that the cartridge boot code is going to be robust enough that it's not really going to matter what the sort of environment it runs in is like. So I'm guessing we can just sort of emulate this IPL by just taking those first bytes here, this cart offset, and just trying to execute, or moving those into memory somewhere and then trying to execute those. So the first thing I want to do is I want to just look at this data. So let's go ahead and open up the ROM in a hex editor. So I'll go ahead and open that. nice 32 meg file that's going to open really quick, and we'll go and switch that to hex mode. And that'll take a second. Here we go. Let me sort of maximize that. All right, so this just looks like a bunch of data. Now, if we go back here and we look at, so this starts at OX40. So let's go ahead and go there and just see if this looks like MIPS code. Yeah. So this is actually where things start to get interesting from my perspective, where I'm going to start learning stuff, because I'm actually fairly unfamiliar with MIPS. But I'm guessing, as with any other kind of CPU architecture, there's going to be lots of different kinds of MIPS. So I'm guessing that we need to look up this VR4300 specifically. If we can find a data sheet on that, then we're in really good shape. So we know that it's called NEC VR4300. So if we Google for NEC VR4300, we get some Nintendo 64 information. This is a cost-reduced derivative of the 64-bit MIPS Technologies R4300i. Cool. Some references. We're looking for a data sheet, and I'm not seeing one. Let's actually just add data sheet to this. And this first one looks pretty good. NEC User's Manual for the VR4300 TM 64-bit microprocessor. That looks like a match. Cool. Let's go ahead and look at the document, look at the copyright before we move any further. Doesn't look like this is confidential. I think I'm okay to stream this. Notes for CMOS devices, don't care about that. Actually, quite a lot of this we don't care about. I want to find a table of contents. Don't care about revisions. Purpose, introduce the architecture. Pipeline operation, that'll be interesting. I'm hoping we can get away with ignoring the fact that there's a pipeline and that there's probably a cache here as well. In fact, I want to see if that mentions that. Yeah, memory management system and cache. Hopefully we don't have to deal with that for quite some time. One other thing that I'm kind of thinking with this emulator is that, so when you're doing emulators, you generally have sort of two ways you could do things. And they're generally called high-level emulation and low-level emulation. And high-level emulation will emulate sort of the high-level workings of something. So in the right now we're going to be doing a high-level emulation of the IPL-ROM. We're not actually going to be running the IPL-ROM, but we're going to do hopefully the same thing that it would have done, right? And that's sort of the difference between high level and low level. Low level means you're more accurately modeling the hardware, and while you get more accurate results, you tend to have a couple problems with it. One is it ends up being more computationally expensive to actually run the code that you write. So a lot of emulators that are going to be doing that won't be able to run in real time. You can do it for older systems like C64 and NES and stuff, but even when you start getting up to Super Nintendo, you can start dropping frames when you're doing accuracy profiles. In this case, for simplicity, because that's the other problem when you do low-level emulation, is that it's a lot harder to do. In this case, I would really like to try and do it high-level and then maybe move to low-level later. But high-level is, I think, more than good enough for us to learn quite a lot from doing this. But in any case, we found the contents. So we have characteristics, ordering information. So cool. This is actually where you could actually buy it. This is probably quite old. Actually, I want to look at that copyright again. 1996, 1998. Ooh, 1994 even. From MIPS. Yeah, because the architecture is probably older. 96 and 98 would have been the different revisions of this document. And I'm guessing those are revisions of the document, maybe to include different models, but this model of processor probably wouldn't have changed just because of all the silicon fab overhead you would have had to gone through to produce that other piece of silicon. So we are interested in, where are we? CPU register, CPU instruction set overview. That looks good. 39. So I'll just Google this because it doesn't look like I can link from the PDF. Go ahead and find that. Go, go, go. Next, here we go. Each CPU instruction is 32 bits long. MIPS is a RISC architecture, as I understand. There are 3 instruction formats. There's an immediate, jump, and register type. So in any case, it looks like 31 through 26, looks like these are going to be 5-bit opcodes here. Or sorry, math. 6-bit opcodes. Maybe I did have it right with 5. Yeah, 5. Different kind of ops. The instruction set can be further divided into following groupings. Yeah, so what this is saying is that each instruction is going to be 32 bits wide, and different bits in that instruction are going to be allocated for different things. So our CPU, what it's going to do is it's going to read 4 bytes at a time, and it's going to look at this. It's going to look at these different kinds of bytes. But I'm guessing, because I think what it's telling me here is that these are the different instruction formats, but then depending on the op, that's actually how this will be interpreted. But at least we know that if it's going to be an immediate type, RS and RT are probably the source and something else registers, probably the different registers that this will operate on, and some immediate value. It's going to be 16 bits, so that'll be kind of interesting when we have like a 32-bit load. Maybe you can't do that. Jump type is going to have an op and then the target, which is 26 bits. That's kind of crazy. R type, op, and then I guess, again, these 2 registers it goes from, maybe a 3rd register, and whatever these are. I guess we'll find out as we start reading. Yeah, T, target. That's definitely what it is. Thanks, guys. Instruction set can be further divided into following groupings: load and store. These will move data between general registers. Computational. Instructions perform arithmetic, logical, and shift, blah, blah, blah. Then jump and branch, which is going to be used for jumping around in the code. Coprocessor instructions. Interesting. Perform operations in the coprocessors. Coprocessor load and store instructions are I-type, as opposed to CP0 instructions. CPZ instructions are not specific to any coprocessor. So that might be interesting. Coprocessor, in this case, I think refers to, like it says here, floating point operations. I believe there's an internal floating point coprocessor in this piece of silicon. And yeah, and then it's the system coprocessor, control memory management and exception handling facilities. The memory management thing will be pretty important to us. We'll see if we actually need to do exception handling for quite some time. Special instructions perform system call exception and breakpoint exception operations, or cause a branch to the general exception handling vector based upon the result of a comparison. Oh man, reading datasheets is fun. Yeah, what we're actually interested in is I would love to get a list of instructions by byte, or organized by opcodes. Let's see if we'll get anything like that. Actually, I'm guessing that there might be an appendix with that, so we'll go back to the contents. Pipeline, memory management system. Got some hardware virtual memory, that'll be fun. Visualization interface. A lot of this, of course, is not just for software developers, but for hardware developers as well. Hardware guys. JTAG interface, that's fun. Interrupts, power management, CPU instructions set details. Here we go. Code bit coding. I'm still going to look for an appendix. No, it didn't look like there was one there, but probably that chapter 16 is what we're after. 363. So we'll do this. And we'll go through this a lot. There we go. All right. Okay, lots of stuff about how to read this. Skip that. The latter part of JRRA1's comment looks useful. CMIPS run might be pretty good. I'm gonna look here a little bit more and see. Here we go. Here we go. Now we're getting somewhere. So what we're looking for is, yeah, there are these 6 bits. The first bits that I see here, first 6, is going to be A0. I'm really bad at binary, so I'll actually have to look that up. Typed AO, oh my gosh. So 1010 and then 00. So this is going to be what it looks like our value is going to be. 101000. Go back to our data sheet and try to find that. If any of this looks like an instruction, we're going to be really, really happy. Confer 1010. So this beginning part of doing emulators, or actually quite a lot of doing emulators, ends up being pretty slow. But that's what makes the fun stuff worthwhile. Domain 64! I just said that because you said N64 dev into house. Actually, chat, if any of you are knowledgeable about MIPS instruction and coding, this could be really useful. I'm looking at A0032048. And that, it'd be cool to know what that instruction is. We are literally just scanning the data sheet till we find it. Is that CMIPS run book? CMIPS run. It's actually great. Chat's helping out. If this is available as a PDF, that's fantastic. I'll keep scrolling through this. Oh, here we have a MIPS green sheet. That looks pretty interesting. Oh, hello. Hello. Thank you, chat. This looks great. That was Ernest, I believe, pointed that out. Also, is that Crazy92 says that endiness might matter? That is absolutely true. We'll see if it actually does. I don't know if it will. 101000 looks like SB something. I know the bunny in Super Mario 64 is called MIPS. Not very helpful though. But I didn't know that. Is that the one you catch in the basement? Is that the one you're talking about? Yeah, so I dropped out of college. So all you guys who studied MIPS in college, good for you. I wish to have gotten that experience, but I didn't. So if endiness mattered, then what we're looking at is not going to be A003242048, which would be, I guess, the big endian representation of this. If it were little endian, then we would be looking at 48 first, but we'd only be looking at the last bits of that, which I believe is going to be like, is that like the same? If you do 4/8 into binary, we're going to be looking at 0, 1, 0, 0, 1, 0. 0, 1, 0, 0, 1, 0 right here. It's either going to be, yeah. Someone says, dude, I don't mean to be a dick, but use obj dump. That's not being a dick. That's super helpful. This is some of this stuff I'm not really familiar with actually doing because I've always just done all this by hand like I'm doing now. So if you got any suggestions like that, then great, shout them out and I'll try that. Is it bin utils? ROM should start with 803.71240. Oh yeah, that's up here. Byte swap probably just because, well, I'm reading, yeah, Little Endian. So let's go ahead and find a MIPS disassembler. The only reason I didn't jump to a disassembler first is because I was kind of worried that like there'd be differences in the different kind of architectures, but maybe the disassemblers are going to be quite helpful with that. Hopefully there's Mac binaries. I am on a Mac. What is online disassembler? That's something I haven't heard of. Oh, that looks fun. Hey, this could be rad. All right, whoops, Entor. If we have MIPS here, MIPS 4300, sweet. Let's see if we can just copy some bytes out of here. We're starting here. Let's go ahead and boop. No, unfortunately, we got all that extra stuff too. How are we going to copy this out? TJS, yes, I did go over that earlier. That I read somewhere that it starts booting from an IPL ROM. If you actually know where to get that IPL ROM, we could actually start working with that instead. But I thought that we would do like a high-level emulation of just copying the code. So I know that we're looking at this. We start at 4.0 because that's where the IPL ROM will start copying from. So I at least know that. And yeah, there you can definitely see Legend of Zelda byte swapped here. Definitely. Keep shouting stuff out in the chat, guys. I really appreciate it. It just helps all of us just sort of reach the end goal. Remember, I'm learning as well, and I want to just kind of one of the reasons I chose N64 is because I don't have any experience with it. So people who do have more experience who want to pitch in, it's all super helpful. Does Emacs not have block select like Vim? I don't know. If it does, I don't know what that is. Rectangles. That sounds like what you're talking about. Rectangle mark mode. So I actually love this that you guys are helping out. This is awesome. Oh, whoops, it typed it in. Oh, that's awesome. That's pretty funny. Rectangle mark mode. How do you use this? That's how you use that. We can just copy out of there. No, because I needed to do that apparently. Oh, really? Oh, really? I do actually know that this ROM works. It's not a bad ROM, even though it looks byte swapped. Again, I think that's anyiness, because if the ROMs, like when you say it started with that specific number, was that like an integer representation of that number, or was that also like, was that corrected for anyiness? Because I would be guessing that it's this should actually give us instructions. Yeah, maybe this is actually being displayed in doesn't actually make any sense. I guess this should actually say Legend of Zelda, like it should be readable. So maybe it is strange that this is all garbled and stuff. Yes, TJS, I think you're correct. Yeah, I'm going to go ahead and do that dd command that JRF suggested, just so we can get... so let's go ahead and dd conf. Is that supposed to say swab? Is that swap bytes? dd conf. Is it swab or swap? Because I'm guessing you mean swap. But I can understand if it was like swap bytes that it might be written that way. Conv, there you go. Yep, conv is swab. Cool. In file is going to be this, and output file is going to be the same thing. Endian swapped. Did not like this. Oh yeah, because I did. Whoops. Need to escape these spaces. Really now. Let's go ahead and let's do this. There we go. So let's go ahead and open that now. Yeah, so now we can see Legend of Zelda. So I did actually find it interesting that what was it? John Milksmell says, of course, ROM is just a representation of the memory. It'll be stored in whatever endianness the platform uses. So I guess in this case, if MIPS is big endian, then it would have been stored. But it's still weird because it should have been byte for byte the same. Like ediness would either matter only at like bit level, you know what I mean? And then it shouldn't matter because it's usually the same at that on that level. So I'm a bit confused at why this would have made a difference, because it feels like every like 4 bytes would have had that swapped. So I'm a bit confused about that. But in any case, if we start taking this code here now, where's my rectangle? Select a bunch of bytes. So now we're actually getting what sort of looks like some code. Again, I'm new to MIPS, so if it looks strange, then that might be something to that. Okay, J.001 says some old copiers would byte swap like that. Okay, then that might actually make sense. If you're doing 4 bytes at a time, and then it's just reading them and writing them, then whatever system that would have run on could have affected the endiness there. But it looks like we actually have, some stuff. So we're going to add some stuff, and then we're going to branch to this other location. I don't know what this data here would be, but I guess it doesn't really matter, because if we're going to be branching over something here, it could also be that I didn't tag enough data on here. Anyway, it looks like our first instruction is add I, which is pretty cool. Crazy92 also says third instruction looks not like an instruction. And so one thing that I am aware of on MIPS is that I believe because of the way the pipelining works, right after a branch, whatever comes after that, because of the way it's pipelined, I think it's if you take the branch, again, we'll learn more about this when we actually get into the emulator, but if you take the branch, the instruction after is still going to be executed, which is weird then that this would look like that. Let's see if we just switch this. Oh, we didn't get 4200. Well, because I know we're jumping over this, but I thought that would still be executed anyway, just because of the pipelines. If anyone knows more about this than I do, please shout out, because I would love for us to all learn from that. Let's go ahead and just copy some more in here. So it still doesn't look like an instruction, but the other ones seem to be disassembling, at least to something. Interesting. Well, what we want to do is we want to start actually emulating this. So I do believe that we've actually hit some instructions, and it's going to be interesting to see how we handle this. So what I want to do now, I want to look at how much memory this would have had, and I also want to try to find a memory map. And what this is going to be about, for those of you unfamiliar with memory mapping, so a CPU is really just this kind of really quick on that comment. Someone earlier said this is just metadata up there in the ROMs. This might not actually be code you're looking for. It may not be, but it should be, because I believe from what we read, I believe it was in here. There's a few checks and copies. The cartridge boot code, card offset hex 40 and onward, should have actually been valid memory, or should have been code that we pull from the ROM. So I'm guessing everything before that is our metadata, and that's sort of, at least this is metadata, and the stuff above, maybe. Hard to say. There's probably also going to be some documentation we can find somewhere about what the rest of that data actually means. But for now, Actually, we could look at that just to see if the rest of the data we're pulling out is fine. But I do want to talk about memory mapping really quick. NC4 programming memory mapping. So again, for those of you guys that are unfamiliar with, sorry. So TJS also piping in with some more interesting information. I'll get to that in a second. Yeah, so for those of you unfamiliar with how the hardware works at this level, so the CPU is kind of just this sort of dumb device that's just going to be effectively pulling data and pushing data. Pulling bytes out of what it thinks is memory and pushing bytes into what it thinks is memory. Now, what's really cool about this is that that's all it has to do, really. Like it's its own unit, and you only have to worry about it doing those two things. The problem is that when you want to interface it with other peripherals, such as the other coprocessors in this system, or anything else really. And so the way that's typically done is there's usually some additional hardware that's external to the CPU. In a case of a system like this, it's usually going to be in that RCP or another one of those kind of chips. And what that will do is it will say, well, if you write to byte 43, the 43rd byte of memory, instead of actually pushing that to memory, I'm just going to take that byte you wrote and I'm going to send it to this other hardware. And this is called memory mapping. And in this way, this machine that just reads and writes bytes can also interact with hardware by when it thinks it's writing to memory, it's actually communicating with other pieces of machinery. And so when I look for a memory map, what I'm actually looking for is literally what different addresses go to where. And the reason I'm looking at this now is that if we're going to start trying to execute some of this code, we need to know, if this code is going to be going into RAM or ROM or something, we need to know where that's going to be from the CPU's perspective. So when we start, if we ever get to like a read or write instruction, we need to know where that was going to or coming from. We need to know that if we're going to, take some code out of the ROM and dump it somewhere, we need to know where that would actually have been, according to how the processor will see it. And I also know that MIPS is going to have, at least this CPU is going to have some memory mapping hardware internally, but that's usually going to be for paging. Things like this memory, this chunk of memory is going to be code and you can't write to it, that kind of stuff. And also just reducing the address space of certain operations. So this is actually pretty cool. It doesn't look too terrible. Yeah, here's our memory map. COP can touch this onwards, meaning it can change the physical address. Okay, I know what that means, I guess. Really quick, TJS 90241 is saying that the code that we're looking at is actually valid code, but it'll just spin infinitely after it realizes the checksum has failed. There's a series of security checks akin to a chain of trust that starts all the way up from the PIF ROM. And this is really good information. It totally makes sense. So what he's talking about is a lot of these older consoles actually had sort of, kind of copy protection. And from what I can tell from what he's saying, the startup ROM will do some CRCs on the data in the cartridge, and we'll find, set up the registers to specific values. And then when we start running the code in the cartridge, it looks like what he's saying is that this will just end up in an infinite loop, because if we haven't set the hardware registers to the exact same values that the PIF ROM would have set them to when it finished executing and when this code started executing, there would be some parts of this code that then would just sit there and go in infinite loop and not run any more of the code. And so to counter that, we would generally need to, I guess, either find that PIF ROM. We can do a quick Google for that and see if we can actually get a hold of that. Or we'll need to set all of the registers and probably also some parts in memory to match what the PIF would have ended up with. So this is awesome stuff. So thank you for sharing. Really cool that we would have to learn this. So kind of a quick thing, I guess. If we didn't have this awesome chat and people helping us out, I guess we would have to learn. If we we're going this blind, like we are really, I guess we would have to learn from like a forum. Go and ask someone about that kind of thing. Crazy92, someone linked it earlier in the chat. I think I may have missed that. Let me scroll up a bit. I see a link to a disassembler. I see a link to the green sheets. I don't see any other link to that ROM. But let's go ahead and look for that. Let's look for a PIF ROM. Some questionable things. Oh, did I miss that link? Thanks for joining us, John Milkspill. So I can see that you're quoting that someone found this, and I don't. Oh, yep. No, you're right. I see what you're talking about. Yep, you did find it. Cool. Yeah, so it looks like we have actually found that ROM somewhere, thanks to TJS90241. That's going to be a hard number for me to remember. So at this time, I'm actually going to take a little break. I'm still going to be recording and everything, and I'll be back in a sec. I'm just going to, get a drink and, yeah, just take a little break. Hey guys, just kind of getting back from a little break. I spent the break getting myself a glass of water, or well, particularly a bottle of water, and also researching more into this PIF realm stuff. One of the problems with trying to find and trying to use a ROM like this is we don't know where it came from. We don't know if we can redistribute it, and if we want other people to use our emulator, those are both problems. So thanks to TJS, I'll just call you TJS from now on, we were able to find at least something that looks like a ROM. As you can see, I've pulled it up here, and I've also done some disassembly to it. Again, I had to byte swap this too. But this is starting to look like some code, even though there's some random stuff interspersed in here. One problem I have with this is that, again, we don't know where this came from, and it's going to be hard to try and redistribute this. So what I've been doing now is I'm sort of poking around the code for existing emulators, and I don't really like to, go around in there too much. But the nice thing is that a lot of people have, solved this problem before. In particular, the one I'm looking at is Sen64. I also dug around in Mupen 64 Plus, and I'm just kind of looking to see how they handle this. It's a bit hard to find where this thing will actually start executing code. I'm fairly unfamiliar with these other projects. I mean, these are just other N64 emulators. Blackpond says, can use some demo scene N64 ROMs. I think those will have the same problems that we're going to face here with any ROM, is that those will also, if they were going to work at all on the original system. Yeah, sorry, that came from the chat. Can you use some N64 ROMs? Yeah, TJ says you can use this ROM, but he's responding to the demo scene N64 ROMs comment, where you can use those ROMs, but still, in order to get those to work, we need either the PIF ROM to have done its job or to have emulated the job that it was doing. So I'm just kind of looking at what other emulators are doing to handle this. So of course, I didn't see any sort of references to the PIF ROM, just digging around sort of the data files. Yeah, Blackpawn, again, thanks for the demo scene ROMs, but I think that they're going to have the same problem where they're not going to boot either. I mean, they might, not. I guess maybe your point is that they won't deadlock because that is part of that whole circle of trust thing. So it probably would be possible to use those. But I also think that this is a problem that we're going to have to solve anyway if we want this emulator to be useful. And even though it might not be the most exciting thing to do right away, it's probably something we're going to have to deal with pretty early on. So if anyone in chat is more familiar with these projects, I'm just going to keep digging through them on the stream just because to show you guys just what I'm doing. But again, all I'm looking for is how do they handle this problem? How do they either circumvent the PIF or have they implemented it themselves? What's going on. So I just went into Mupen 64 Plus's code. That emulator's code is split up because they've done a good job in their emulator architecture in that they've split everything up into a bunch of different modules. And I have, it looks like core is where we're going to end up finding that one. They have a front end. TJS is the dev of Sen64, so I guess he would know. I didn't realize that that's who that was. That's pretty funny. Oh, yep, that's totally the case. Just saw the name there. That's awesome. So actually, TJ, if you have any sort of way where I can find how you're handling this, that would be really cool. I did search for PIF in the repo, and I found a bunch of stuff about there's a CIC seed for cart given the ROM data, but when I searched for get CIC seed, the only place where I saw this function used was in the controller stuff, and I have no idea what that is. Also, yeah, thanks for tuning in, by the way. I think that's pretty cool. So I'm not entirely sure where to look. I guess your entry point is here in sen64.c. Yeah, sen64 main. Yeah, from. So does Sin64 rely on having that ROM come from an external source? Like, do you provide that when you use that emulator, or is that something else? Or do you guys have, I don't know, I guess some other way of circumventing this? You can look at in the VR 4300 manual for the startup sequence. I'll look at that, but I'm guessing that will still rely on this ROM being somewhere. Back to our datasheet here. Let's see my prior comment on the address. Right. Okay. So I guess what you're telling me is that you rely on having this be provided to the emulator, which is cool. That's a fine way to do it. And yes, I would actually like to try and find the startup sequence from the datasheet instead of from your emulator code. As useful as that would be, I kind of want to try to go through that process without using too much other emulator code. So all we're looking for is yeah, the startup sequence here. I wonder if it's called startup sequence. No, it's not. Don't feel like it'll be in general. TJS is looking for it as well. Thank you. Pretty stoked at getting all this help for the chat, but from the chat, by the way. Thanks, guys. Initialization interface. I guess it does go over cold reset, soft reset, power on reset, so it might be in here. I'll go ahead and look at that anyway. My gut feeling, though, is that this is going to be more from a hardware perspective. Yeah, like here, it's not if it clocks, major part initial stage registering may retain. After reset, the processor is bus master and drives the sys8030 bus. Guys, we're taking to coordinate reset stuff. I want to see what else happens. Section 9.2.1 for initial processor states. Okay, we're almost there. Cool. Yeah, here we are. Here we are. Power on reset. Cool. Looks like we found it. You probably found it a little bit first, but it feels real time to me because of chat delay, so that's cool. Power on reset is used to completely restore reset the processor. As a result, TS, SR, and RP bits of the status register and EP30 bits of the config register are cleared to 0. Good to know. ERL and rev bits of the status register and B bit of the config register are set to 1. Upper limit value 31 is assigned to the random register. EC bits of the config register are assigned to the contents of the div mode 10 pins. So that's going to depend on the wiring, I guess. May not be that important. All other internal statuses are undefined. Good to know. So not that bad. Cool. So what this basically means is that we can start emulating the processor, basically set this state here. We'll probably... Section 641 for initial cold reset exception. Okay, so that's probably where... Yeah, here we go. After power supply to the coprocessor has stabilized, after power on reset, assert the cold reset signal active for the duration of 64,000 master clock cycles or more. So I guess this is telling us that if we were to incorporate this in our design, then this is what we would have to do. From an emulator author's perspective, we need to assume that this has been done. Sounds like what it's going to be about. And then, yeah, he said section 641 for initial cold reset exception. Give sample exception handler operations for the following exception types: cold reset, soft reset, NMI, remaining processor exceptions. Okay, so here we have the cold reset, soft reset, and NMI exceptions are always vectored to these specific locations. And now I believe in the chat, TJS also mentioned where this ROM would be mapped to, and I believe that address matches. Just looking through the chat to find that. Yeah, it's right there actually. Yeah, BFC0. Yeah, there we go. Cool. So thanks to TJS, now we know exactly what's going to happen when we start it up. We're going to assume that a certain number of master cycles went by while cold reset was held high by some other piece of hardware. That drops low, or I'm probably mixing up high and low. It doesn't really matter for us. And then code execution starts executing at this address. And then this is exactly where that PIF ROM was mapped to. Pretty cool stuff. Cool beans. Now, I run a really quick look at that memory map that we found earlier. And just kind of see if that also matches up with what we've got here. Whoops. Window management is still an unsolved problem in computing. Or at least I'm not good at it. Yeah, now that I look at this memory map, I'm not sure if this was the most valuable thing, but where were we again? BFC0. According to that, we're in the middle of ROM here. So it could actually be that this, because what I'm actually wondering here is, so we know that the PIF ROM is going to be mapped to this location, and we can't unfortunately distribute that ROM, but we could actually start executing from it, and see if that works. So I know it's going to be mapped to this, but one of the things that I'm wondering about in this system is whether or not that memory always stays mapped there or not, or if there's like a register somewhere that will turn that mapping on and off. Because I know in a lot of other systems, that's typically the case. You usually want to free up that memory, and so you're able to sort of bank that out in the memory mapping hardware. But you know what? We can actually worry about that later, and we can just load the ROM and map it here and see what happens. So let's go ahead and load the ROM next. Let's actually go back to writing some code. I know it's been forever. What do we call this? Rustendo 64. That's great. Cool. So we'll do that. I'm going to go ahead and write a function for loading binary files. All right, so function load bin. We'll do that. Now Rust has a really actually kind of cool type signature to use for file names and stuff. So we're going to go ahead and look at Rust file open. Because there's a specific trait that I liked that they had in here. Yeah, they did this. So take any type of P where P is an asref path. Not important that we understand how that goes, but the important thing is that, whoops, does that go on the, yeah. Important thing is that our path will be a type P. And we'll just return a vec of U8s. Might actually be annoying to deal with those as U8s because we'll be doing that. Actually, we can abstract the indiness. We'll be okay. We'll be okay. Yeah, so we'll dump that. Oh, whoops, I copied over that code. Let's do that again. And we're actually just going to return the file buff here. In Rust, it's implicit that the last expression you write, if you don't have a semicolon, will just be the thing that's returned. Copy this back out. Yeah. We'll actually make this the second argument, and we'll make the PIF ROM. Let's cool, we'll do that. And now, of course, this will, oops, let PIF from is read bin PIF file name. And Rusty Bicycle is saying instead of and path, you'll need to do path.asref. Yep, fine. Thanks. That makes sense. And then and mute. Or isn't that what that does? Well, we'll see what the compiler tells me when I'm done with that. Run. Actually, PIF. Bin. File name. Go back to here. Oops. And we'll go to our PIF. Just gonna do some magic behind the scenes things. Actually, we'll see what the compiler tells us. Path, yeah, is that stdio path? Or is Rust path? std path. Yeah, that's what you're talking about. Mute. There you go. Nice call. Move asref here. Following along the chat. If we're doing nth here, and this is going to be a mutable iterator, this will probably break the iterator when we do this. Is my guess. It'll probably move there. Right, yeah, you're saying to change the index of nth after that because this will clobber the arg. So I'd rather actually just repeat this both times to be more explicit about what we're doing. All this will be written better later, like error handling and stuff. Cool. So that didn't work because we didn't have a thing here. Nope. Where did I download that to? 1 second. Okay, I just had to move stuff around and didn't want to flash anything on the screen. That's just gonna just place that in ROM's PIF data. Cool. So now we've read both buffers, and now we can actually start looking into how to execute this. Now, before actually executing any of this, this will get kind of fun. We need to actually start modeling the CPU. So this is where things sort of start to get interesting. I'm just going to dump a bunch of stuff in this one file, and then we'll split stuff out as things actually start taking shape. I just find that to be an easier way to work in general. I'm also just going to do a quick commit while we're at it. Cool. So yeah, so oh wow, we've been doing this for 2 hours. Well, that's fun. I guess what better way to spend a Friday night, right? Okay. So let's get into the CPU. Make a little struct. Gonna do this kind of oopy, I guess. Oop is actually a pretty good way to write emulators, I found. I mean, the way that you model things with OOP is you model these sort of, mutable components that interact with each other over time, and that tends to be pretty close to what's happening with hardware, where in OOP you have message passing in the form of function calls, whereas in hardware you have it in terms of, or you have it in the form of actual signals changing on buses. But in general, we'll have probably like let CPU is, or let mute CPU is CPU new is the way to do that in Rust, and then we'll do CPU.run or something. We'll figure that out. Yeah, so I'm not entirely sure what that's going to look like yet. We're going to implement stuff for the CPU. Function new, give us a CPU. Can give us a CPU with some to-do stuff here. So now I actually want to look at what kind of registers we have for the CPU, because before we start, actually running any code, we need something for that code to operate on, and that's going to be our internal hardware registers. So cool. So I'm really happy. Again, thanks to TJS for getting us this information about where stuff will boot and everything. But now I want to actually look at our registers. Man, that zoom is helpful. Okay. So if we look back into contents of our datasheet, this is again the datasheet for the VR4300. We want to look at, got internal block configuration, CPU registers. I'm actually going to go here, section 1.4, just to go ahead and look at that. That block configuration might be fun to look at anyway on our way there. There we go. Yeah, so we have a clock generator, some kind of system interface with the data address. Those are going to be buses, and then some, I guess, control wires. Our instruction data caches, CP0 was that coprocessor 0, which had the, I think this is called transition look aside buffer, which is our internal memory remapping stuff. The actual execution unit, this is the thing that's going to be pulling instructions. Our different instruction address, which is going to be our program counter, and I guess some pipeline control stuff to move all this stuff around. So that was kind of fun to look at. Yeah, coprocessor has the memory management unit, handles exception processing. Cool. An instruction address calculates the effective address of the next instruction to be fetched. It contains the incrementer for the program counter PC, so PC is going to be one of our registers. So let's go ahead and do that now. Add that here. Reg PC. Because I believe all of our addresses are 32-bit, I think the PC is going to be... Oh wait, we have all the registers right here. So the program counter I was about to say is probably going to be 32-bit, but it looks like it's going to be 64-bit, which is cool. Yeah, it's going to be U64 reg PC. What other registers do we have? 32 64-bit general purpose registers and 32 64-bit floating point operation registers. Cool. So that'll be, do this, constant num general purpose registers. That'll be a U size is, yep, I did forget a colon, thanks. Size, that's going to be 32 because we're going to have 32 of these. So I'll add these in the same order that the datasheet specifies them in. So we're going to have our general purpose registers, GPR regs. Oops, yeah, well, too much of, there we go. Lots of small mistakes I'll make because I code in way too many languages on a daily basis. GPR regs is going to be an array with, I believe it's U64 colon num GPR. I may have those mixed up. We'll figure that out in a sec. So there's the GPR regs. We're going to have the FPR regs, which are going to be the same thing, but instead of U64, they're going to be F64 for 64-bit floats. Hopefully our float model is going to be the same with our host CPU. Probably be okay. In addition, the processor provides the following special registers: 64-bit program counter, PC. So yep, we got that. 64-bit high register containing the integer multiply and divide high order double word results. Okay, that makes sense. So let's call that reg muldiv high, or we could just call it reg high just because that's what people will know it's called. Also going to be U64. There it is, C++ habits die hard. Oh yes they do, yes they do. There's also a reg low, same thing, whoops, U16, another habit. Call that LO, just a match. We have a 1-bit load link LO bit register. I guess we'll find that out. I'm tempted to model that as a bool, but I really want to make it an enum. We'll make it a bool and we'll change it later once we know what that will actually contain. We'll call that LO bit. Reg LO bit. Bool. Enum type. 32-bit floating point implementation revision register, FCR0. Let's call that FCR0. Make that a U32. And then we have the floating point control status. That makes sense. FCR31. Two of the general purpose registers have assigned functions. R0 is hardwired to a value of 0 and can be used as a target register for any instruction whose result is to be discarded. So that'll be interesting when we actually start implementing things to ignore register 0. R31 is the link register used by JAL and JLR instructions. It can be used by other instructions. Make sure that other data used in calculations does not overlap with the register used by the JLR instructions. So I guess a link register, judging by what I know from other CPUs, is going to be like a return address kind of thing. Like when you, I guess these are jump instructions, jump AL or jump ALR are probably jump always and jump always relative is probably what that stands for. And so these are probably going to jump execution to another point in memory, but then store that location to go back to later. And that's it probably just is hardwired to use that register, which means you can probably still read and write that register as we would any other register at any time. It's just that you should be careful because those instructions will always use that. So interesting that that's not in a stack, so I might be wrong interpreting that, but that's what I'm thinking so far. And here we go. So we have R0 equals 0. Yep, 31 link address. Cool. A little bit. Implementation revision. Control status. Looking good. It has no program status word. That's fairly interesting. Usually there's a register called PSW or something like that, program status word, and that usually has all your bits for like, oh, I did a compare and my compare was of my two values were equal. There's usually a bit in a register that tells you that, so you can actually read it or write it, or yeah, that needs to be stored somewhere. This is covered by the status and cause registers incorporated within the system control coprocessor. Interesting. So it's actually part of that block. That's pretty cool, actually. So maybe we need to model that next. And then, yeah, then we're into the CPU instructions. Let's actually go and look at that. I want to see what that looks like. Oops. Four types of coprocessors. CPU0 is an internal system control coprocessor that supports a virtual memory system and exception processing, as we've read many times before now. CPO converts virtual addresses into physical addresses, selects an operating mode, kernel supervisor, or user mode, so I guess we get some kind of memory protection in MIPS. This is pretty cool. And control exceptions. It also controls the cache subsystem to analyze causes and return execution from error processing. Coming to think of it, this kernel supervisor or user mode, I'm guessing the N64 software will never actually use any of those. It might, but I don't think there's like an operating system that's actually running as such. Typically for these old consoles, I mean, you don't like have networking hardware, so there's a lot of sort of security risks that aren't really risks. So you really don't need that kind of separation. You're also not doing multitasking, so you really wouldn't need these extra kind of operating modes. You're just going to run on the bare metal. CPU register of the VR4300 is the same as that of the VR4200 because the VR4300 does not have a parity check function. However, its parity register 26 and cache register do not practically operate. Interesting. Okay, so these are different register names. So I'm guessing that there's, it mentions that there's a CPO register. And when I look at this, there's all these different numbers. There might be like an internal location you write to, or maybe a specific register that you interact with. And what you actually do is like set the number of this with part of that register and then do a read or write with another register or something. It's a bit hard to tell from just that. And the CP1, I guess, we'll also have to implement. That might be fun. So we might have to do a little more reading on this CPU register. The details of the registers related to the virtual memory system, something else, used for exception processing. So I am a bit confused at how this fits together. Because it says it contains registers. It could be also just be that there are specific instructions that read those and write those specifically. So maybe those will come up later. That could very well be. Hard to say if that's how all that fits together right now. But in any case, we're going to need to have these registers available. Okay, so these are the same table. I don't know what these colors mean. Oh, okay. Different things that they're used for. Memory management, exception processing, and for future use. So that's reserved. Almost said reversed. Oh, I'm actually getting from TJS MTC0 and MFC0 right from CPO registers. So I guess that's the mechanism I described. But so now that we have heard of MTC0, because I didn't see that anywhere. Yeah. Oh, okay. Yeah, you're talking about the actual instructions. Gotcha. Loads of contents of the word of the general purpose register RT of the CPU to the general purpose register RD of CPO. Gotcha. MC0 and MCT0. That would make sense. So let's go ahead and look at that. Also from chat, TJS is saying, if I recall correctly, the first few instructions in the PIF ROM are MCF0, MTC0 instructions, which would definitely make sense if they're trying to set up how we actually read memory in here. So this is the disassembly I took of that ROM. Where is our scroll bar? That was weird. And this kind of looks all jarbled. U4Z0. Let's go ahead and look at the unscrambled one. Oops. I did do a swapped one as well. Let's go ahead and look at our just grab a bunch of bytes. 463. Yeah, again, so this is without being byte swapped, and it looks just kind of like nonsense. And then also the other way that I had it also looked like nonsense. So I'm a bit unsure what we're looking at here. Very strange. Maybe if we look back into our data sheet, unfortunately this didn't have, where was that green sheet? So I guess this didn't have the December is probably configured for little endian, since IRC most whips configuration little endian ROMs are big endian. I wonder if we can change that in that disassembler. Endianness is going to be a big problem here, I can tell. But might be fun. I guess we can change it here. Little. Let's go ahead and look at. This looks like gibberish. If we copy these again. Yeah, this is boot code. This is actual code here. Okay, cool. So it looks like this was meant to be, or the ROM itself is in big endian. Disassembled, we have an LUI instruction. There's an MTC0 instruction, which I definitely expected to see really early, and then LUI and ORI. I don't know what LUI or ORI is, but it's probably like load unsigned immediate or something. And then ORI is probably OR with immediate value. And that actually makes sense with the registers that I'm seeing here. Actually, that makes perfect sense if this is load immediate, because we're loading register T1 with this value, and then it looks like we're storing that value in number 12, which is probably register 12 of the C0, and that would definitely make sense. So actually, this is really cool, because this is sort of our first win where we actually saw code. It's really funny that it took us this long, but sometimes that's what happens, especially if you've never done this before. Awesome. So yes. And then, again, we're going to load into T1 with immediate, and then we're going to OR that value with this, do something else with it. This is probably additional CRC stuff, as TJS was mentioning. Fancy. Cool. So what we've learned from this is that whenever we read from these ROMs, we're going to be doing big endian reads. So that's good to know. Another thing we've learned, again, is that this is actual valid boot code, and MTC0 is what we're going to be using to communicate with the coprocessor 0. Now, in modeling that CP0, I think I'm just going to make an additional structure for that. So let's go back and see if we can find that list of registers for COP0. Cool. Yeah, here it is. Index random, yeah, these guys. So I guess I basically more or less just copy this table. Yeah, I think this will be interesting to fill out too. We'll get to that in a minute. Thinking out loud here. I'll also rename these really quick, just to make it match all these other registers. Because I'm guessing there will be other things than registers that we'll need in the CPU state. Maybe not, but we'll see. Maybe not. Yeah, because I think what I'm going to do is I'm going to just model these registers like as is. Like I'm just going to have this many registers laying around. It's weird that it says some of these are reserved, but then in this table, oh no, okay, 21 through 25. Never mind, I misread the table. Cool, yeah. So I'm just actually going to model each one of these things here, and then I'll have like whenever we interact with this, we'll like write an interface to the CP0, like write register, read register, and that will do the mapping for us. Because generally, when you're writing an emulator, you do want it to be. There tends to be a balance historically where it's like this balance between ergonomics and like ergonomics / expressiveness, and then the actual speed of the emulator. I'm guessing this is probably going to be fast enough once the compiler has done its job optimizing everything. So for us, we kind of want this to be more ergonomic and sort of look nicer. Okay, so I guess we have an index register. What size were these? I know I read that out loud, but I forgot it already. I guess they're going to be 64 bits. Because all the other registers were. And if we're going to read and write to them with these things, then they're going to be 64-bit. Let's just do that and then see if we have to change this later. Reg random. Reg entry low 0. Reg context u64. Reg page mask u64. So you can see I'm converting the like camel case naming convention here to the more rustic one, which is where you have these. This is called snake case. Reg wired 264 reg bad v adder reg counts. And some of these as well, like I see a count, which is going to be like a timer compare value, or sorry, timer count. It's actually probably pretty likely that we're going to want to change this to not actually be a value, a register value like this. We're actually going to have a timer object beneath this as well. And then whenever we read and write to this, instead of reading and writing this value, we'll just communicate with that object directly. That tends to yield fairly nice code, I think. Reg entry high. We can also go back through and reorder these as well to group them more meaningfully than the grouping here, if we so choose. Again, that's another benefit of having abstracted the indexing from the actual registers themselves. Cause. Yeah, I forgot this handles exceptions as well, so that makes sense that was there. Reg EPC, I don't know what that is. Oh, exception program counter. There you go. PRID. Config. The load linked instruction address display. Who knows what that is? Reg. Watch low. Yell at me if I missed any. If you can read the data sheet, that is. Reg X context. Some reserve stuff. Reg parity error. U64. Little star here. These registers are defined to maintain compatibility with the VR4200 and not used with the hardware of the VR4200. So these actually, let's not model, because I believe that's the thing it referred to earlier, where it was saying that these are effectively not used by the hardware and only there for compatibility. So we'll model those in terms of the mapping. We'll just have it like return dummy data or something, but useless to actually try and emulate that if it's not going to happen in our system. Yep, so then we have reg tag low and reg tag high. And reg error, the error exception program counter. I have no idea how that's going to be different than the regular exception program counter, but I guess we'll figure that out. So the CPU is going to have a CP0 inside it. That we know for certain. We're going to end up doing this. Equals CP0. New processor into its initial state. I'll actually do a CP0. Okay. The initial values for these are probably going to be pretty annoying to fill out, or maybe not. Maybe we can just set them all to 0. We'll have to see. I bet the config and stuff will be different. A lot of that kind of thing, like what is the startup state of this is going to be scraping that from the data sheet and just some good old-fashioned reading. What's cool here, though, is that this is an off-the-shelf component, so we do have access to the data sheet like this. So that's pretty rad. Yeah, so this was going to have CP0, so we'll just call it CP0. Cool. I at least know what that's going to be. It's going to be CP0. Good stuff. So now I want to go back to that startup state that we saw earlier, because yeah, we're also going to have hard and cold resets that we might need to deal with. Actually, this is a good question again for TJS, if you remember. So, of course, there's going to be a hard reset when you turn the system on, but is the reset button on the console actually mapped to a cold reset or a hard reset, or whatever they were called. Bad at terminology. But I'm guessing that'll be the cold or soft reset or whatever it's called. It's unlikely we'll be able to find a useful schematic for the system, just because there are so many lines and buses. TJS says no, JRA. Reset is wired to the PIF. I'm not exactly sure what that means. It triggers an NMI on the VR4300 followed by a hard reset. Okay, so I guess for us, the hard reset part is the really... Gotcha, okay. So I guess you get an NMI when you push it, and then when you release it, you probably get a hard reset. If I understand you correctly, JRA. I'm more just curious to see if we ever have to do the other reset, if we ever have to emulate that. May not be something we need to worry about. In any case, hard reset is something we need to worry about. I was just thinking about that because we're going to do a function hard reset. And we're going to do in mute self. And this is going to have the same thing. Little to-dos. The NMI is a reset warning. Try hitting reset Mario 64 and it will do this blinds effect. Oh, good to know. I figured that when you said NMI, I figured it would be something like that because you don't want to be like in the middle of writing save ROM or something when the reset button's hit. I don't know if you have enough time to actually deal with that, but I guess 0.5 seconds is a lot of cycles. A lot, so might be okay. TJS says you can get away easily by implementing the hard reset for now. Good. That's what I was hoping. Yeah, so we're looking at the startup state again. Again, the TJS mentioned that in the chat, so I'm going to look up where that was again. 9.2.1. So we are pretty well rolling now. It's pretty cool. TS, SR, and RP bits of the status register and status and config. Were those registers in here? They must be because the names match. Okay, they were called power on reset and cold reset. I was saying hard reset and cold reset, but power on and cold reset. So I'm actually going to rename these. Just to more match the datasheet. Because the thing is, it's good to I like to match these things to like the datasheet more than I like colloquially matching them. Like if everyone in the N64 community referred to it as hard reset, I would still rather call it power on reset, just because like if anyone else from outside that community ever wanted to use this piece of code or use it as a reference, this would be less ambiguous. And I don't think the N64 emulation community, at least the emulator developers community, is that large. So I think we'll be all right. They'll know the difference. Yeah, so what this is telling me is that the only real known states are these registers that are really only part of the CP0 are reset to known states, and all other registers are going to be whatever. And that's actually pretty sensible. That sounds correct. I'm going to go ahead and read a little more of this, but cold reset is used to completely reset the processor, and again, this has sort of the same information. We do have the software set again. And again, only registers. Yeah, processor retains as much state information as possible. All state information except the following is retained. And we have, again, these things that are only related to the CP0, it looks like. Cool stuff. Yeah, so it looks like then these are really all we have to model. The rest is just going to probably be set to zeros. So I'm just going to go ahead and what I'm going to do is I'm going to make the this new function just return a CP0 where basically the whole structure is zeroed out. And then the power on reset is going to be the one that actually sets these to meaningful values. And I think that's an okay to model, or okay way to model it. The other way to do it is do like a let mute ret is this, and then call power on reset on it before we return it. It's up to semantics. I'd rather just have this just return the object, and then make sure you do a power on reset. Because like, I kind of like that these objects would be treated as the actual hardware. So you as a consumer of the library would treat it as if you were the consumer of the actual silicon if you were implementing it into a design. So in general, in software, I'd like not to do things like this. But I think this is a per case basis where this is sensible. Just because like you don't typically, when you're designing a library or something, you don't want to like build an object or return an object that is not prepared or not ready. You don't want people doing anything like invalid or making assumptions based on the things that you actually give them. But again, I think because we're trying to model hardware, I think it's okay to do this. Anyway, someone can yell at me if they disagree. So let's just copy out this. Place all this. 0. Oops. And looking good. So we'll do the same thing here with CP0. I'll do a search replace here. 64 with 0. Good. And then we'll do the power on reset. So here, again, because like none of this seemed to be preserved on or like in known states, I think the only thing we actually have to affect here is this. And we'll do a power on reset on CP0. Oops, that's actually self. There we go. And then we write this stuff. You could also, depending on how sort of correct you want it to be and robust you want it to be, you could also, like on power on reset, a lot of emulators like to just fill all the registers and everything with random values, which more or less, it's not, I wouldn't actually say it correctly emulates hardware because you really can't know what that's going to be, and usually you get a lot of like FFs or something, like it's not actually that random, but it's good for people who develop against emulators, because what you actually get is I mean, you just want to rely on the fact that you can't rely on that data, and making it random helps you enforce that. JRA1 says, have you given any thought to how you'll handle graphics HLE or LLE? I know it's early days yet, just curious what you think. So I believe I talked about this earlier, but I really want to do HLE first. And then maybe we switch later, but my guess is that we'll still be able to get something playable just with doing HLE. And I think it'll be a lot easier. I have this this vision of my head of this just like super, super broken Mario game or something like Mario Kart where everything's all jumbled and awesome. I just think it'll be really fun to see. And I think if we do LLE, then we'll just, I think it'll take us a lot longer, and I don't think it's much more valuable for this format, for this project. Again, maybe we do that later. Who knows? Who knows how this project will go? So TSSR and RP bits of the status register in EP, 30 bits of the config register are cleared to 0. So to find out what these bits actually are, it looks like we need to actually look at the status register. 0A1, good luck. Thank you very much. Looks like we'll need it. Just opening another one of these. Yeah, status register. Search for that. Give it a moment. Oh, here we go. Control status register bit assignments that we're after. That looks like exactly what we want. Here we go. Control status FCR1. Is that the same one though? Is that the because that was a floating point control register. I'm not sure if that was the same one that we're looking at. Where's that zoom? Oh, the zoom was fun. Oops. So this is telling us TS, SR, and RP bits of the status register and E of the config register are cleared to 0. TS, SR, and RP bits. That's a I'm not sure what bits those actually were. I might be looking at the wrong diagram here. So again, that's floating point. Let's go back to the contents. This is FCR0, and I thought it was going to be the control register here that was referring to. Or maybe I just totally misread that. Sorry, status and config registers. I keep saying control register, but I really am trying to look for status and config. That's going to help. There we go. Or whoops. That was that one we looked at earlier. Here again, we mentioned the RP bit of the status register. Let's search for RP bit. Try to find that. Because I just have, I believe we just have no idea where that RP bit lives. Coming up on 3 hours now. It's kind of fun. Could look at the coprocessor instruction, CPO instructions. See if those give us any clue. Navigating data sheets is an art that I have certainly not mastered. I don't know if anyone has. Okay, so these are just telling us, like, loading those registers. Wasn't very helpful. We do have this memory management system. So here's CPO registers. Was it the table we found? Or was that after? I don't know. Let's go see. Hello. CPO registers and the TLB. Format of the TLB entry. Oh, here we go. At least we have page mask entry high register. So it looks like we're going to find it here. Here's the index register. Looks like we got these big old blocks that are bits. The random register. TLB write random instruction. It'll be fun to figure out what that is. The wired register. Okay, config register. And here we have the color set stuff here as well. So at least we know stuff for the config register. So this is actually another case where, so I know that we've taken like the config register and made it EU64. First of all, it looks like it's a lot smaller than that. It looks like it's 32 bits. The other thing is that, excuse me, this sort of encoding here, where it's like the 32-bit encoding and the different bits mean different things. When you're writing an emulator, one of the things you can totally do is, instead of model the actual, this same representation, you can model like, oh, this was actually an enum with 3 different choices. And then when you're reading and writing the value, then you can actually do that translation yourself. And I tend to prefer that. Of course, it's more writing, but you get a lot of like type safety, and in general, I just think it's a nice way to do it. Cool. Yeah. So I guess we can break apart the config register first. Just reading the data sheet. Sorry if I'm being quiet. This is interesting. The values of EP and BE areas can be changed only when initialization is executed in the non-cache area immediately after cold reset and before a store instruction is executed. Interesting. The operation is not guaranteed if the values in these areas are changed at any other time. I guess that makes sense though, because if this is configuring, I don't know what EP and BE are yet, but here we go. There you go. Yeah, so it sets big endian memory. Yeah, little endian, big endian. So I guess that's reading from memory, whether or not this is going to interpret that as big endian or little endian. EP sets transfer data pattern, single block write request. So this actually makes a lot of sense then, that these would be available to write only right after startup, because I'm guessing that the values in these registers are going to affect how all of your other bytes, being written and read from the CPU are going to be interpreted. And you don't want to do that, in the middle of writing code. You don't want to switch endianness. Could be fun though. B bit of this register is changed by using the MTC0 instruction. Insert 2 or more NOP instructions and or instruction other than load store instruction in between the MTC0 and load and store instructions. If the B instruction. I'm guessing actually because this is known to be default values, and we've seen that the ROMs are in big endian form. I'm guessing these are actually never touched by the PIF. You would have no need to. Cool. So I was going to go ahead and write this and start splitting up this config register. But I'm actually, it has been about 3 hours, and I'm actually getting fairly tired. So I think I'm actually going to cut off the first episode here. And yeah, probably continue this maybe tomorrow. I'll try to give you guys some notice before I pick it up again. But I will not touch the code other than a commit that I'll do really quick here until then. So I guess that concludes this first episode. The journey begins. So thanks again, guys, for tuning in. And again, thanks again, guys, in the chat. TJS, JRA, a couple other guys. Crazy, you guys know who you are. Thanks again for all your help and just shouting out when I was doing silly things or whatever. It's really cool to be able to interact with you guys and have you guys help out. Chemical Nova, can I ask a really quick question? You can ask a really quick question. Waiting for the question. Zorg666, I really enjoyed this. How do you plan on announcing when you'll stream? So my Twitter is probably going to be the primary way of announcing this. My Twitter is twitter.com/Ferris tweets now. I'll write that in the chat really quick. I think that works. Yeah, so that's my Twitter. If you follow that, then you'll see all the updates. Ernest, thanks to you. It was really entertaining. Thanks. Really appreciate hearing that. Chemical Nova might be a silly one. How do you get motivated for such a big task? So that is kind of a good question, actually. Because I do know that this is going to be enormous. At least before we get anything decent running. I think emulators are just really cool. And you know what I mean? The size of the task is intimidating to me if I have to do something, or if, you know what I mean? I think I'm primarily motivated just because I think it's just really cool. I love N64 and I love, all these old systems that gave me a lot of joy when I was younger. I think it's really cool to, now as I'm older, be able to understand these on a deeper level. And I just think this will be really fun. So I don't know, I guess I like emulators, and that's what makes me motivated to do this. Miku Hutsunen, good stream, looking forward to more. Thank you. I appreciate that. Chemical Nova, I look forward to watching you do this. Thanks again. The Lock, super cool stream, thanks. You're welcome. Chemical Nova, great answer, thanks. Good, glad you think so. So I guess I'll be doing Q&A at the end of all these, because that pretty much runs. Ernest, Ferris runs on nostalgia. Nostalgia and Coke. Yep. I'm a biological machine that metabolizes sugar into software and caffeine. So if you guys have any questions before I go, now's probably a good time. Oh, also, I don't have the YouTube stuff set up, but I did record this whole stream. Miko Hudson, what emulators have you worked on before, if any? So of course I've done Chip 8, and I did I did another one in Rust actually. That was the audio unit of the Super Nintendo. So it wasn't the whole Super Nintendo. That's actually an emulator that scares me more than N64 in terms of like being a daunting task, because that's one of those ones where the system itself was so weak that a lot of the cartridges had special chips in them, and emulating all of those to be able to cover your whole space of games is really tough. Also, BeastNest has done a really good job. Move away 000. Yeah, sorry, I just gotta quit soon. Yeah, again, I will totally put this on YouTube. I haven't set all that up yet, but I'll announce all that on my Twitter and everything. And I'll update the links for the next episodes. As you can see, there's a link on the top of the screen that show like my Twitter and all that other stuff. So I'll have the YouTube one in there too. Yeah, so Mika Hudson, the other one that I did was the audio unit of the Super Nintendo, and I'll link that too, because that's open source. And I did that in Rust. There's a couple parts, though, that I need to fix, because I think they were sort of ported from Blarg's code, if I remember correctly. It was a while ago. I do give them credit in the attribution, but I'd like to change them just to write it in more of my own words. That was the envelope code I definitely did that with, and some of how the CPU was structured. But the rest of it is all mine, and that's very accurate as far as I know. I think the only ROMs that I found, the SPC files that I found that don't work with it, are the ones from Star Ocean, and that may have to do with the fact that it streams samples, or maybe that wasn't Star Ocean. Maybe that was Tales of Fantasia. Can't remember. Zorg666, the VOD should show up on Twitch pretty soon. Yes, I forgot about that. Twitch does automatically record these. I'm also recording them myself just so we have them archived, because I know Twitch likes to delete these. But yeah. Yeah, so this is that emulator that I did for the audio unit of the Super Nintendo. Just if you want to check that out. It is also in Rust. I did it originally in C++, but I ported it to Rust. Unfortunately, it only works on Mac right now because I rely on some other abstractions to abstract the audio stuff that aren't done yet. But if we just fill in those in with, if we fill in that abstraction with Windows and Linux implementations of the audio stream stuff, then it'll all work. The emulator itself is cross-platform. So yeah, I guess that's everything. Once again, guys, thanks a lot for tuning in. I really appreciate the support while doing this. Thanks again, guys, for the guys that helped out. I'm really looking forward to doing the rest of this project, and I'm really glad that people actually watched when I started this. So yeah, thanks again, guys, and I'll see you next time.